All right, everybody, what we're going to do is move on a little bit. We talked about the types of bonds last video, where we looked at the chemical bonding, and then we went through the types of energy, and then we looked at the last time we looked at this, we looked at the types of bonds, the covalent, the ionic, and metallic. So what we're going to do is look a little bit more how we know. All right, so how do we know that we have a specific bond? Is looking at something called the electronegativity. Again, we've done that before. Electronegativity is the ability for atoms to gain electrons, or how well they do this. So we're going to look a little closely at a guideline to see what type of bonds we're actually going to form when we do this. Okay, and we can look at the electronegativity difference, the pulling difference between two elements, and this is going to be really important going forward. So definitely pay attention to this as you go. All right, so we're going to look at the electronegativity difference between the two atoms. Okay, and we're going to plot this on a number line. So we want to think of the difference in electronegativity, which is the change in electronegativity. That's going to be delta En. Okay, and we're going to plot this on a line. It's going to go from 0 to some higher number. Okay, and again, the highest possible number you can get is the difference between cesium at 0.7, okay, and fluorine at 4.0. So I guess 3.3 would be the highest you could get, and that would be all the way over here. All right, so anywhere along the lines, elements will have anywhere between those two. You'll be plotting on the line. Now, the name for this attribute, this difference, we can think of it as ionic character. So if you're towards the low end of this line, then you'd have low ionic character, which would be here. This would be low ionic character. Up here would be high ionic character. So it's how much ionic character you have, and we're going to go over that in a minute. All right, so the first thing is what happens if you have very little electronegativity difference. So we're going to use chlorine as an example. Now, chlorine, if you had two chlorine atoms, so we want to assume that we have two chlorine atoms here, okay, and let's those two chlorine atoms were bonded together, okay, so this would be a chlorine nucleus, and this would be a chlorine nucleus. And what they'll do is when this happens, when you bond two nuclei together, like so you bond two elements together that are exactly the same, they're going to have exactly the same electronegativity. So they'll be pulling on the electron cloud of the other element very evenly. All right. So if you take 3.2 electronegativity and 3.2, okay, because each element is pulling evenly on each other's valence electrons, you then are going to have an even sharing, an equal sharing of electrons. Okay. And the electronegativity difference would be 3.2 minus 3.2 is 0. So anywhere in this zone of a very low electronegativity difference means the pulling difference of each element is basically even. And that would be like an even sharing. Like, so say you were sharing a meal with someone and you split that meal 50-50. If you did that, a 50-50 sharing, would you would get exactly half the meal. So again, this symmetrically shaped electron cloud gives the indication that each element is pulling on those electrons evenly. So it's stretched out between both atoms. Okay. If you go on to a bigger difference in electronegativity, and again, if you're sharing the same nonmetals, you'll see these elements are identical, you would pull identically. When you have two different nonmetals, okay, in the case of H and Cl, all right, in this way, you're going to be slightly different in this case because each element pulls differently. So if you have H here, okay, and Cl here, you're going to be pulling at different rates or different strengths. And you can see hydrogen pulls at a 2.2, but chlorine still pulls at a 3.2. So what's going to be happening is you're going to see that the electron cloud becomes distorted. The bond, the electrons actually spend more time over around by the chlorine than they do by the hydrogen. Okay, and what happens in that case is you get this lopsided electron cloud where you get a partial negative on this side. Now, the reason is the case is that because the bond is being pulled in that direction towards the chlorine, and chlorine will take a partial negative charge, where on the left side, okay, you will take a partial positive charge. Now, this little sign here, that little sign is the Greek letter sigma. That means partial. All right, so don't get all wrapped up in that. It just simply means that there's going to have a negative side to it, and that's going to have some type of a positive side to it. So you're going to get an unequal sharing here. Okay, and the key is unequal sharing versus equal sharing. Okay, because you have different nonmetals. So two different nonmetals will be in here. And again, On this side of this number line, you're typically going to be in the non-metallic area. Again, these are non-metals. All right, and your electronegativity difference is again 1.0. 1.0 on this line is anywhere in between the 0.5 and the 1.7, where 0 is anywhere from 0 up to 0.5. All right. Now you can see as you pull harder and harder on one side. Now let's just use the most extreme. If you go to the most extreme, we're going to find a situation where you have sodium and chlorine. Now, for the first time, we're going to introduce a metal to the bond now. Okay. Now a metal, since it has a very low electronegativity of 0.9, and we're still dealing with a very high electronegativity at 3.2, that difference is so large, okay, that you're literally going to transfer an electron from the metal to the non-metal in this case. Okay, so I just want you to see the progression. So an electron literally goes from the metal to the non-metal in that case, and the electron is ripped right off. So you could see the progression from a very even sharing to uneven sharing to just a transfer completely, right? So in this case, you'd be sharing a meal evenly. Here you'd be sharing a meal unevenly. In this case, one person takes the whole meal. Okay, and again, you're looking at that difference of being 2.3, okay, and that 2.3 is a big difference, greater than the 1.7. So in here would be about 2.3. Okay, now what do we call this kind of thing? What do we call this? We can use a lot of these ideas to isolate a certain type of bonding. So what we're going to do is we're going to call covalent bonding a type of bonding where you're sharing electrons. Okay, and we can break that into two types. We can break that into nonpolar. Go back a little bit. Okay, so in this case, we're going to use we're going to call this nonpolar bonding. Okay, so this is going to be called nonpolar. Okay, and this is going to be called polar. Okay, and so again, nonpolar and polar will be two types of covalent bonding, where here, I keep messing up my slide. Let's do that again really quickly. Sorry. This would be nonpolar, okay, where this would be polar, okay, and over here would be ionic. So again, you're using these numbers here as guidelines to where you would have that type of bonding. But I want you to focus in on same nonmetals would be up in this zone, different nonmetals would be up in that zone, metal and non-metal will be up in that zone. Okay, now the word polar, again, polar means poles. Okay, so when you have poles, again, that's going to be a negative pole, okay, a minus pole, and that's going to be a positive pole. Okay, and again, polar means opposites, polar opposites, if you've ever heard that word before. So when you have two poles, you're going to have a negative pole, a positive pole here, and a negative pole here, where here you have no poles. So no polar means you don't have two opposite ends. Okay, really important, okay? So how do you actually do this? We can review this a little bit. So what we're going to do is basically to practice this. So to practice this, we're going to simply we're going to determine the electronegativity of each element. You can look that up in the table. Again, you can use table S, okay? You're going to find the difference in electronegativity. So you'll simply subtract the two elements, right? Subtract, okay? And then you're going to label the bond polar, nonpolar, ionic based on that chart, based on the number line, right? So if you're less than 0.5, then you'd be nonpolar. If you're greater than 0.5 and 1.0, 1.7, you'd be polar, okay? And again, ionic. But again, nonpolar is going to be nonmetals, polar is going to be nonmetals, ionic is going to be a metal. That's the best way to do it. Okay, and then you're going to assign the plus and minus to the elements based on their electronegativity. The higher the electronegativity is the element that gets the negative. All right, so let's just say you had an OH bond. Well, if I look at those electronegativity, let's say I look at these examples. Okay, if I go to the OH bond, I'm going to look at oxygen is going to have a 3.5, hydrogen is going to have a 2.2. Well, because this is a 3.5, you're going to pull harder on that side, so that's going to get the negative. Oxygen is going to get the positive, right? So the electronegativity difference is 1.3, and you're going to have a polar bond. There's the negative pole, there's the positive pole. Okay, carbon and chlorine, let's look those up. Okay, we got 2.6 versus 3.2. In this case, chlorine would get the negative, all right? Carbon would get the positive. Again, the higher electronegativity always gets the negative. The higher electronegativity gets the negative. Okay. Again, the difference is 0.6. So this is going to be slightly polar. Okay. And we can call that a polar bond, right? Potassium and chloride. Again, potassium fluoride. Again, this should give you an idea. When you have potassium, you know you have a metal. We're going to go to 0.8 versus 4. 4 gets a very strong negative. Potassium's got the positive. Big difference in electronegativity of 3.2. Okay, in that case, you're going to be ionic. Again, you're going metal, non-metal. Again, you're thinking two different non-metals. Again, two different non-metals. All right. Now, Mg and O, again, it should kick out to you here that you have a magnesium and an oxygen, magnesium being the metal at 1.3, 3.5. Again, 3.5 gets the negative. This becomes the positive. Okay, then you have 2.2 as a difference. Again, you guessed it, you're ionic. Okay, and we're going to be a metal and a non-metal again. Okay, again, metals get the positive, non-metals get the negative. All right. All right, and last but not least, nitrogen-nitrogen bond. Okay, again, nothing going on here. You have an electronegativity difference of 0 here, right? No poles. Okay, so there's no poles here, no polar. With no poles, you get electronegativity of 0, and now you'd have a non-polar bond. Again, you have even sharing. All right, so that's the way you would determine your bond type. What type of bond do you have? All right, important to know. All right, so that's going to be something we're going to go. Again, this would be covalent, covalent, covalent. Okay, if you wanted to add that to your list. All right, so let's look at covalent bonding a little bit more closer. So that's the first thing we're going to do is our covalent bonding. So let's look at that first. Okay. Okay, so covalent bonding, what you're going to do is you're going to share pairs of electrons between non-metals. Okay, gotta know that. Right, non-metals are going to be covalent. Okay, covalent means to share because they have high electronegativities. Okay, they're going to overlap their valence orbitals. They're going to share their valence orbitals as the nuclei come to attract each orbital, and it's going to usually give you 8 valence electrons. Usually, again, this is a guideline. Okay, you can share 1 pair, 2 pairs, or even 3 pairs of electrons between 2 atoms. So it gets fairly complicated with that. So you can have, X could bond with X with 1 pair. X could bond with X with 2 pairs represented by the lines. Okay, you can bond with 3 pairs according to the lines. So these are different options that we can do. We'll get into this a little bit later. Okay, 2 main types. We have non-polar bonds and polar bonds. We did a little bit of that before. Okay, and we're going to form molecules. This is so important, huge. Something that forms a molecule is a molecular substance that equals covalent, okay, which equals sharing. I say so really important that we know that sharing and covalent are really important things together. Okay, so some examples of molecules. You'll see non-metals touching in chlorine, water, and ammonia are examples of these things. Okay, a couple of things, examples of everyday molecular kind of substance. Sugars, any carbon compounds, any organic. Okay, so organic stuff. Okay, plastics. Okay, living organisms are all covalent and exist as molecules. So that is a lot to do with this. Organic is carbon compounds. All right, really important. Any of your non-metals, you're looking at, again, if you're looking at the periodic table, you're looking after the staircase, you're looking at this area of the table and hydrogen. Really important, this section and hydrogen. Okay, so which of the following are molecules if we had to do this? Well, let's see. We're looking for non-metals. Carbon and oxygen, are they non-metals? Are they up in that corner? Yes, they are. That would be a molecule. Magnesium, nope, that's a metal. Okay, so that won't be. Potassium and bromine. Okay, potassium's over here. It's a metal. Okay, that will not be a molecule. NH3, N and H, that's a non-metal. That's a non-metal. Okay, so we're going to have a molecule there. Okay, carbon compounds, carbon, hydrogen, oxygen, non-metal, non-metal, non-metal. Yup, that's also a molecule. Okay, calcium. Calcium's a metal. Nope, but this is non-metals. Okay, so this would not be a molecule. So your molecules are only the ones that have non-metals in them. Okay, really, really important. They're going to ask this question a lot in your bonding. All right? All right, so 2 types of bonds, 2 types of polar bonds and non-polar. Just look at them a little closer. Okay, again, you're going to share electrons for a non-polar bond, but it's going to be an even sharing. Again, no polar. Okay, so you have an even sharing. You have an even share, right? Each chlorine atom shares evenly across chlorine and chlorine, evenly sharing across. So both atoms pull evenly. You have an electronegativity less than zero point 0.5. You have no plus or minus ends to the molecule. Again, a chlorine and a chlorine bonded is a 3.2 and a 3.2. They bond evenly. So this would be an evenly shaped molecule. Okay, all diatomic elements, your Brinkelhoff. Okay, don't forget your Brinkelhoff, Brincl, and F. All of these are non-polar. Okay, really important. Okay, so it's very limited, right? Because most of the time you're going to have elements bonding with other elements. Okay, so in a polar bond you have unequal sharing, so it's unequal versus even. Okay, the higher electronegative atom pulls on the electrons more, so it becomes negative. Okay, again, when you pull electrons to help you become more negative, the other atom is positive. Okay, you have an electronegativity difference greater than zero point 0.5. Okay, and new molecules can now attract each other. That's going to be interesting. So again, take a look at this versus that. Now we have hydrogen on one side that has a 2.1 electronegativity versus a 3.2. Okay, and in that case, this is going to be the negative side of the molecule or the negative side of the bond. This will be this positive side of the bond. Okay, and you'll eventually see how this difference is 1.1. And again, it distorts the cloud. We have a negative sign on that side. Now, what's the consequence of this? Why is this such a big deal? Well, what we find is that if you have another molecule of HCl next to another molecule of HCl, because one side has a negative side and a positive side, if you put that up against another molecule, the negative side of one molecule can actually attract the positive side of the other. Okay, and this is a little intermolecular force, and that's called a molecular force. So you can actually have multiple molecules that actually connect to each other like little magnets because they have those little ends to them. Okay, so now molecules can attract each other. And that's going to be a big deal with the chem and the physical properties. Okay, and we're going to see this in class when we do this. All right, so a big deal. Please review this if you need to. Okay, and it's a really important group. So you have ionic, polar, and nonpolar. Ionic and covalent. Covalent is split between these polar and nonpolar bonds. All right, so hang in there. Have a great day.